Hi ladies, this is Mrs. Blaufuss and this is lesson 5.2. It's evaluating and graphing polynomial functions. So the first thing I want you to do is look at your note sheet. These are available online if you don't have them printed out. So on your note sheet you have 5 key vocab terms, and the first one is polynomial function. So again, you need to remember what we did with quadratic and linear functions because it's going to really tie into what we're doing here with polynomial functions, both with factoring and with graphing. And in this lesson, we're going to focus on end behavior and how it's related to the function equation. So your first vocab term is polynomial function. And a polynomial function is a function written in the form a sub n times x to the n power plus the next term times x to the 1 lower power, and so on, all the way until you get to just a constant term. So a polynomial function is a function of monomial or sum of monomials. In a polynomial function, exponents are always going to be whole numbers. That means it can be 0 or any positive integers, but it cannot be a negative integer, and it cannot be a decimal or a fraction as an exponent. If you look at this polynomial function, the leading coefficient is the very first coefficient associated with the largest exponent. So in our standard polynomial form, our leading coefficient is a sub n. And then our constant term is the term that we have that does not have an x associated with it or a variable associated with it. So in, again, this generic form, it's a sub 0. Then our next term is degree. And this deals with the power you're taking x to. So it's the largest exponent. And that's represented by n. And then the last one is end behavior. And the end behavior describes the graph as x approaches infinity or as x approaches negative infinity. So if you look at this parabola that I have just sketched here, if you look at just the parabola here, the one in this mustard color. So on this parabola, look at the x values. So as x approaches infinity, our y values also approaches infinity, and that's what we're looking at when we're looking at end behavior. If you look at x as it approaches negative infinity, y approaches infinity. So the y values are still increasing even though the x values are decreasing. So we're going to focus on that, not just with quadratics, but with polynomial functions as well. All right, let's look at these first couple examples. And in this example, we're deciding whether the function is polynomial or not. And if it is, we're to write it in standard form, state its degree. Our degree is our n. State its type. So what does the n mean? So if n is cubed, for example, it would be a cubic polynomial function, a quadratic. And then our leading coefficient is the last question. So our leading coefficient is our a sub n term, so that's the coefficient in front of our largest exponent. All right, so let's look at the first one. Remember, with a polynomial function, all exponents have to be whole numbers. So if you look at this very first exponent, 2 times x to the 1.2 power, 1.2 is not a whole number. Therefore, this is not a polynomial function. look at the second example, 0.32x minus x cubed plus 71. All of these exponents are whole numbers, so this is a polynomial function. So to write this in standard form, we want to start with the largest exponent and the coefficient associated with that. So in this case, it's negative x cubed. We don't have an x squared term. So then our next coefficient and exponent is 0.32 x, and then lastly our constant term. So in this example, the degree is 3, because our largest exponent is 3, and that means that this is a cubic polynomial function. For a list of several types of polynomial functions, you can look on page 337. And it gives you the names of polynomial functions related to their degree. Okay, and then the last question is, what's the leading coefficient? And this is our a sub n, so this is our first coefficient, which is -1. Right, this next example is from your textbook. It is not on your note sheet, but just on a piece of paper or where you're keeping your notes for this video, please try these ones on your own. Same as the example that we just did. Decide if it's a polynomial function. If so, write it in standard form, state its degree, type the leading coefficient. The first one is a polynomial function. It's already in standard form, and it's to the power of 4, which is quartic function, and has a leading coefficient of 1. The second one, yes, is a polynomial function. It's quadratic. In standard form, it's pi x squared plus 7x minus the square root of 3. And the leading coefficient is pi. The third one is not a polynomial function because x to the -1. -1 is not a whole number. Therefore, this is not a polynomial function. And then last one is not a polynomial function because of that 2 to the power of x. In a polynomial function, you need to have the variable as the base and the whole number as the exponent. All right, in this lesson, we're going to work with a couple different methods as far as substitution goes. This first one is using direct substitution in order to evaluate this expression. So with direct substitution, we are just substituting that x equals 2. We're substituting this 2 right into this function. So f of 2 is going to equal 8 times 2 plus 5 times 2 to the 4th minus 3 times 2 squared minus 2 cubed. And then we're going to evaluate it this way. So f of 2 equals 8 times 2, which is 16. Plus 5 times 2 to the 4th power. So 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. 5 times 16 minus 3 times 2 squared, which is 4, minus 2 cubed, which is 8. now I'm just simplifying in order to evaluate. So that's 96 minus 12 minus 8, which is 96 minus 20. So I get my f of 2 equals 76. So when x is 2, this function is equal to 76. So that's direct substitution. That's what we have done so far. But this lesson is going to introduce synthetic substitution. So I've outlined some of the steps here. So use synthetic substitution to evaluate. We're going to evaluate the same polynomial function. The first thing that you need to do is write this in standard form. So our leading coefficient and our degree are first. 5x to the 4th minus x cubed minus 3x squared plus 8x. And then we don't have a constant term, so I'm going to write it plus 0. And it's important to do that because of how we set up our substitution. So in the synthetic substitution, I'm still looking for when x is 2. So the way I'm going to set it up is I'm going to write out all of my coefficients, starting with my leading coefficient. So 5, -1, -3, 8, and 0. So all my coefficients and my constant term. And I'm looking for when x is 2. And I'm just going to draw a box around all of my coefficients so that I can evaluate. All right, so then my next step is to bring down the leading coefficient, which is 5. And then I'm going to multiply 2 times 5 to get 10. Then I'm going to add -1 plus 10 to get me 9. Then I'm going to do the same thing again. 2 times 9 is 18. -3 plus 18 is 15. 2 times 15 is 30. 8 plus 30 is 38. And then lastly, 2 times 38 is 76. 0 plus 76 is 76. And this is my answer. So that's using synthetic substitution. So we'll do another example, and then I'll kind of show you why this works. So let's do this next example, use synthetic substitution to evaluate. The first thing I want to do is make sure that this is in standard form. And even beyond that, I'm going to write out all of my exponents just so that when I set it up, I have all of my columns filled in. So I've got x to the 4th plus 0x cubed plus 0x squared plus 3x minus 20. And I'm looking for when x is equal to 4. So I'm going to write all my coefficients, 1, 0, 0, 3, and my constant, -20. I'm going to draw a box around that. And I'm looking for when x is 4. So I'm first going to break down my leading coefficient. Then I'm going to multiply 4 by 1, which is 4, and then add 0 plus 4, which is 4. Then I'm going to multiply 4 times 4, which is 16, and then add. Then I'm going to multiply 4 times 16, which is 64. Then I'm going to add to get 67, and then multiply 4 times 67, which is 248, or 268. And then I'm going to add to get a final solution of 248. All right, so now let's look at why this actually works. Because sometimes it kind of helps you understand the process if you understand the why part of it. So if you think of your f of x in standard form, let's just do it with ax squared plus bx plus c. And you're trying to evaluate if x is g. So when you set this up and you list all your coefficients, you have a, b, and your constant c. And your x is equal to g. So bring down your a, g times a, is a times g, and then you're going to add them together. A times g plus b. Now, if you multiply these g times a times g plus b, you get a g squared plus b times g. And then if you add that, add c to that, you get a g squared plus bg plus c. Which, if you just use direct substitution and you substituted g in for your x in your original form, you would get a g squared plus bg plus c, which is exactly what you ended up with direct substitute, with synthetic substitution. Alright, so this next section is about the end behavior of graphs. And again, we're going to look at polynomial functions all kinds, but just looking at this quadratic, which is kind of what we discussed at the very beginning of this lesson. But when you're just starting to investigate these, you want to look at what happens when x continues positive and what happens when x continues negative. How does that affect your y? So in this first example, as x approaches infinity, y also approaches infinity. And as x approaches negative infinity, y approaches infinity. In the second example, when you have a graph facing down, the opposite is true. When x approaches positive infinity, y approaches negative infinity. And as x approaches negative infinity, y approaches negative infinity. So that's our end behavior. Y is our f of x, whatever our function is. So on your note sheets, you have kind of a cheat sheet for key concepts that has a few different types of graphs. A cubic and a quartic and a even powers and an odd powers graph. So in this next example, this is not on your note sheet, but you can use your graphing calculator to graph each of these functions and then describe their end behavior. So try these ones on your own, pause the video while you work. And then you can unpause for the solutions. Alright, so here are the graphs that you should have gotten if you used your graphing calculator. And in the first one, as x approaches positive infinity, f of x approaches positive infinity, and the reverse is true if x approaches negative infinity. F of x also approaches negative infinity. So look at this. These solutions that I've written up here, and kind of compare them to the end behavior polynomial functions, because they should all hold true. So in number 4, for example, we have a negative leading coefficient and we have an even exponent. So as x approaches positive infinity, f of x approaches negative infinity. So here's the leading, or this kind of cheat sheet that you have on your guided note sheet, so you can refer back to that as we go forward. In example 5, we're looking for the degree in leading coefficient. So you'll have to focus on the end behavior. So in this example, f of x approaches negative infinity both when x approaches infinity and x approaches negative infinity, f of x approaches negative infinity. So you're just looking at the end behavior, not really what's going on in the middle. We're just focused on the end behavior. So if this is true, then we have to have a negative leading coefficient, and the degree has to be even. Next one, you see that as x approaches positive infinity, f of x approaches negative infinity. And then as x approaches negative infinity, we can see that f of x approaches positive infinity. So what do we know about the leading coefficient and the degree? Well, the leading coefficient has to be negative, and the degree is odd. And the reason I know that is just by looking back at that end behavior of polynomials cheat sheet graph that you have. It's in the top right corner. All right, the next question that you see on your note sheet is to describe the end behavior of the graph of the polynomial function using limit notation. So this is what happens to f of x as x approaches positive or negative infinity. All right, so let's look at this graph. 10 times x to the 4th. The leading coefficient is even, and the degree is even, and the leading coefficient is positive. Okay, so if you look at your cheat sheet here, we have a positive leading coefficient, we have a degree even, so that's the bottom left-hand corner of that graph. So using limit notation, you're going to say f of x approaches infinity as x approaches infinity. And then also f of x approaches infinity, actually you should say positive infinity, as x approaches negative infinity. All right, on the second one, notice your leading coefficient is negative and your degree is odd. So if you look up at the top right-hand corner, using limit notation, f of x approaches positive infinity as x approaches negative infinity, and f of x approaches negative infinity as x approaches positive infinity. All right, here's our next one. Graph each of the following polynomials. We're going to check our end behavior, but we're going to look at just a bunch of different points. I think 5 is a good number to pick, but you can pick more or less because you really are focused. You want to know what's going on in the middle, but you also want to know what happens at the end. So we'll just pick a few coordinates here. So if our x is 0, that's kind of an easy one to pick. So if our x is 0, our y is going to be -1. So that's an easy one to pick, so I would always pick 0 first. But then you're just going to make a table. So x and y. So let's say that we choose -2 for x, for example. So you want to choose a few negative numbers and a few positive numbers, just so you can see what's happening in the graph. Now you can either use direct substitution or synthetic substitution. It doesn't matter which one is which. So just to review, I'll do -2 with synthetic substitution. So I've got -2, and then -1 as my coefficient, 2, 2, -1. So -2 times -1 is 2. Add those together. Multiply. Here's my coordinate for my y. Okay, so you can do this a bunch of different times. I'll choose -1 this time. Okay, so go ahead and plug in a few different values for your x, a few negative and a few positive. So I did this already, so you can calc these out just for extra practice. But 1, 2 is another point, 2, 3 is a point, and 3, -4. And for all of these, I use synthetic substitution in order to calculate, but you can use direct substitution if you'd like as well. All right, so now you have to plot those points. So I plotted already 0, -1. Now I'm going to plot -2, 11. And it's going to be a little bit off my grid, but that's okay. Just estimate about where you think it would end up. -1, 0, 1, 2, 2, 3, and 3, -4. All right, so when I graph this out, I'm going to sketch in my graph here. Make it as smooth as you can, so it should not be like a whole bunch of points, like a whole bunch of lines connected together. It should be a smooth cubic graph. So check your end behavior of your graph. So my leading coefficient is negative. My degree is odd. So if you look at your cheat sheet, it should look like one in the top right corner, whereas x approaches -infinity, f of x approaches positive infinity, which is true. And then as x approaches positive infinity, f of x approaches negative infinity, which is also true. Okay, so try this one on your own. Pause the video while you work, and then you can unpause for the solution. I'll give you a bunch of points, and you can check your graph. Okay, so here's roughly what my graph should look like. Again, you should plot those points, make it a smooth quartic graph so that it's not a bunch of just pointy mountain-looking like things. It should look more like hills. And check your end behavior. So in this, as f of x approaches -infinity, x approaches negative infinity. And as f of x approaches negative infinity, x approaches positive infinity. Okay, so if you look at the top or the bottom right-hand corner of your end behavior polynomials sheet, we have an even degree and a negative leading coefficient. All right, so that's all for this lesson. So please jot down any questions you have, and we can go over them next time I see you in class. Thank you.